guys. Today we're talking about average rate of change. Before we get into it, let's do a quick review of slope. So if I gave y'all the line passing through -2, -1, and 1, 5. What is the slope of this line? Well, who remembers how to calculate that? Remember, the slope is the rise over the run, right? So the change in y, or the rise, over the run. We calculate that by, well, figuring out what this is. So if we are looking for the distance between 5 and -1, well, that's just 5 minus -1, right? The y value of this minus the y value of that. y2 minus y1 over the x value here, right? 1 minus -2. So x2 minus x1. This might be familiar from algebra. The way we're going to see it written more frequently in this class is using function notation. So f of x2 minus f of x1 over x2 minus x1. That's it. So here, the slope, well, the slope here is, well, what's x2 and x1? We'll call this point x1 and this x2. So if x1 is -2, that guy goes down here. And we're subtracting x1 from x2, which is 1. And then on top we want f of x2, which is 1, and then f of x1, which is -2. So what is f of 1? Well, we can look at the function, right? What's the output at 1? It's 5. What's f of -2? -1. And these guys kind of stay the same. 5 minus -1 is 6. 1 minus -2 is 3. So we end up with 2. That is the slope of this line. Okay, so what does that mean about this function? Well, in words, really quickly, all it really means is from x equals -2 to x equals 1, the function increases on average by 2. So what does this mean? Let's look at the definition of average rate of change now. So the average rate of change which we'll pretty frequently abbreviate to ARC, is the slope of the line through 2 points on a graph. So for instance, let's say we're looking at a nice parabola. like this. And let's say that the points we want to look at are this guy and this guy. We'll call them A and B. So any point on this graph, I'm just going to pick a random one, is going to have the form x and y, but our y value is the output of our function, right? So if this guy is f, then our y value will be f of x, right? So knowing that, if we know that this point occurs at x equals a, what can we say about this point? Well, our x value is a, and then our y value, like up here we had x f of x, here we'll have a f of a. Similarly, with b, our x value is b, so our y value is f of b. Knowing that, and knowing that our average rate of change is the slope of the line running through these 2 points, or this guy, how can we calculate this slope? The average rate of change from x equals a to x equals b is well, remember the slope of a line is the difference in y values divided by the difference in x values. So here we have f of b minus f of a over the difference in x values, which is b minus a. That's it. That's our average rate of change formula. Let's look at an example of this. So say we're looking at this guy, and we have the point 0, 1 and 4, 3. What is the average rate of change from 0 to 4? Well, we just want to find the slope of this line, right? So all we have to do is look at the difference in y values. So f of 4 minus f of 0 over the difference in x values, so 4 minus 0. What is f of 4? Well, the value of the function at 4 is 3. What is f of 0? Well, the value of the function at 0 is 1. We do this subtraction, we end up with 2 over 4, or 0.5. One thing I'd like for us to notice really quickly, if I look at the average rate of change of this interval again, but I accidentally, or whatever, I choose to because I'm deciding to be quirky, let's say I flip the order. What happens? Are we going to get the wrong sign? Let's see. So f of 0 here is 1. F of 4 here is 3. And then we have 0 minus 4. So we end up with negative 2 over negative 4, which is still 0.5. So I've switched the orders here, which gives me a negative and a negative, when before we had a positive and a positive, right? Switching the order will not affect the average rate of change. So it doesn't actually matter which one you choose to be x1 and x2. We just have to make sure that they're lined up, right? We have to make sure that f of x1 is over x1 and f of x2 is over x2, regardless of whether f of x1 is first or f of x2. So here with this function, what's going on here, what this means is that from x equals 0 to x equals 4, the function increases on average by 0.5. So every time we take a step forward in the x direction, we take half a step up in the y. Okay, so pretty simple here, really just a matter of remembering what our formula is, right? Remembering how to calculate the slope of a line and remembering, okay, I'm just looking for the slope of the line between these 2 points. That's it, and knowing how to pull the y values from the graph. All very simple stuff. Let's look at the average rate of change of something symbolically. So let's say we were given a function negative 2 over x squared, and we were asked to find the average rate of change. Well, we don't have a graph anymore, so that's different, but not bad. Let's write down our formula really quickly. So if we're looking for from x equals 1 to x equals 3, then we have 3 minus 1 underneath, and we want to find the change in y values, so f of 3 minus f of 1, that's all. How can we move forward from here? How can we calculate this? Well, we've got to replace less useful things with more useful things, right? So f of 3, not super useful, but we know that f of x is negative 2 over x squared. What can we do? What is f of 3? Well, we've replaced x here with 3, so let's replace it here, right? We're just plugging in. So we have negative 2 over 3 squared. So 3 squared is 9. So we have negative 2 divided by 9, which gives us negative 0.222 repeating, but we can just stop it at 2. So that's f of 3. Now we need f of 1. What is f of 1? Well, again, we've replaced x with 1, so we've got to replace x here with 1. So we have negative 2 over 1 squared. We end up with negative 2 over 1, or just negative 2. All right, so we know what f of 3 and f of 1 are, so let's just plug them in, right? We've got f of 3, which is negative 0.222, minus f of 1, which we know is negative 2, divided by 3 minus 1. We compute this subtraction. This minus negative 2 gives me positive 1.778. We divide by our denominator. 3 minus 1 is 2. So we end up with 0.889. That's our answer, right? The average rate of change of this function between the point x equals 1 and x equals 3 is 0.889. So this one is a simpler function. find the average rate of change of g of x equals negative 2x plus 3. This is a new way of saying what we've been talking about. This is another way you'll see it written. So we're asking for the average rate of change on the interval (1, 3). So saying on the interval 1, 3, all this is asking for is the average rate of change between these 2 points, right? So what this means is that this is just our x1 and this is our x2, right? It's just asking for the average rate of change between these 2 points. The endpoints are 1 and 3, so those are our 2 x values. Let's compute our average rate of change. Again, we know x2 is 3, and we know x1 is 1. So we want our y values there. We have the function g, so we have g of 3 is our first y value, and g of 1 is our second up top. What is g of 3 and g of 1? Well, we just plug in, right, for this x value. G of 3 is negative 2 times 3 plus 3. Negative 2 times 3 gives me negative 6, plus 3 is negative 3. G of 1 is negative 2 times 1 plus 3, so negative 2 plus 3, which is 1. So on top it looks like we have negative 3 minus 1 over positive 3 minus 1. We compute the top. Negative 3 minus 1 is negative 4. 3 minus 1 is 2. We end up getting negative 2. So, just writing this one more time, from x equals 1 to x equals 3, g of x decreases on average by 2. So let's take a look at this in the lab manual and ways that we can apply this. I believe this is our first word problem. We are going to be looking at the average rate of change section. All right, so we're given a function of the population of wild turkeys in Wake County. I had a run-in with a wild turkey in the wild once. It was not that fun. As a function of T years, since there's this legislation put in place to protect them. So we have the graph here. We want to label each axis with quantities in units. So again, this is kind of our first real-world run-in with variables, right? And thinking about what's our independent variable and what's our dependent variable. What is the variable that is changing the other variable? One of these variables, right, either the population or time, is changing with respect to the other one. Is time changing? Is time shifting in response to the population of turkeys? Probably not. That would be crazy. Is the population of turkeys changing over time? Yes. So time is our independent variable, right? Time is independent. It's not going to change for anyone. And our turkey population is our dependent variable. It depends on the time. Great. So when I do word problems, I like to think about what our points are going to look like and what they represent and what our variables are representing. Start off by writing down what our points look like. So our points are going to look like t and p of t. Because time is independent, that's our x value, right? So we have x value for time. We have time and it's in years. And then P of T is our population in thousands of turkeys. Use the graph to find the average rate of change of P from t equals 0 to t equals 4. Well, our formula tells us that average rate of change is going to be, well, our x2 value is 4, our x1 value is 0. We want to find the y value at 4 and 0, so we get P of 4 from the graph and P of 0 from the graph, right? So what is P of 4? Looks like 8.75. And what is P of 0? Looks like 5. Divided by 4 minus 0. So looks like we end up with 3.75 divided by 4. What is that? Let's plug it into a calculator. Looks like we got 0.9375. What are the units here? What does this mean? This is saying that every year between 0 and 4 years, right, after enacting this legislation, the turkey population increased by 0.9375 thousands of turkeys, right? So it's not 0.375 turkeys, it's actually 937 turkeys, right? Let's write that down really quickly. So between year 0 and year 4, the turkey population increased on average by 937 turkeys per year. Use the graph to determine the average rate of change between 4 and 8. We do the same thing. So we've got, why don't you guys try this out, get the number, and we'll talk about what it means. All right, so I got 0.2625. Again, just got these values from the graph, right? The y values of these respective x values. What does this mean? Well, this means that between year, I'm going to shorten a couple of words here to save space, year 4 and years 4 and 8, the population increased on average, I'm going to abbreviate average, by 262 turkeys per year. Okay, so compare these rates of change in context. Well, right, earlier on, right, in these first 4 years, we increased a lot per year, right? Every year we increased by, on average, 937 turkeys, right? And then the second 4 years, on average, we increased a lot less, right? On average, every year we only increased by 262 turkeys. So the rate of change is really fast when we start out, and then the rate of change slows down, right? Gets smaller, it slows here. And that makes sense, right? Because if we look at this graph, the slope of that line is a lot more positive than the slope of this line, right? This is a smaller slope than this one. So our change in population is getting smaller over time, right? It's increasing by less and less every year. So as we increase, right, as time goes on, what's happening to the turkey population? It's getting really, really, really close to what value? Looks like 10, right? Which of course doesn't mean 10 turkeys. Remember, our units are in thousands of turkeys. So we're approaching 10,000 turkeys. What graphical component does this correspond to? Well, what does that look like? What have we talked about that looks like this? That 10. Starts with an H, ends with an horizontal asymptote. Horizontal asymptote. Let's look at the next page. We're not going to worry about F. Okay, so let's say we're looking at this table. We've got the temperature in Fahrenheit over a certain amount of time. So what are our independent and dependent values before we get going? Well, we don't necessarily have variables here, which is fine. But let's still think through, okay, what's my independent, what's my dependent? Well, this guy is, of course, our independent, right? Independent always comes first. Independent is what we're putting into the machine, right? And then the machine spits out something depending on whatever was put in, right? So the dependent depends on the independent value. So, of course, time, whenever we have time, that's going to be always our independent value. Nothing is going to change time. And our temperature is going to change over time. So that's our dependent value. So our time and temperature in Fahrenheit, degrees Fahrenheit. What is our unit on time? Well, that's something we need to kind of think on. We're looking for the change in our dependent value over the change in the independent value. So the change in temperature over time. Well, our changes in temperature over that time, we end up at 82 degrees and we're starting out at 78 degrees. That's our change in temperature, right? What is our change in time? Can we subtract just 1 minus 12? We'd get negative 11. Does that mean that negative 11 time has gone by? No, that's not how it works, right? We need to think about it a little bit differently. So the way folks usually like to do it is think about 1 as 1, right? And 12 o'clock as 0. So we're starting at 0. And as we move forward in time, how much time has passed since we started? Well, at 1 o'clock, we will have passed 1 hour. At 3:15, we'll have passed 3.15 hours? Not 3.15 hours, right? 3:15 is 3 hours and a quarter of an hour, so it's actually 3.25, right? 4:30, do we put 4.3? Again, no, right? 4:30 is 4.5 hours, so 4.5, and then at 6 hours have passed. So now we can think about what our units are. Time is in hours here. You could have also converted this into minutes if you wanted to, right? This would be 60 minutes after 12. This would be, right, 195 minutes later, etc. That will just change the units on your answer, but it's still correct. Okay, anyway, let's think about the change in time. So, between 12 o'clock and 1 o'clock, we've changed 1 hour. right? 1 hour has passed and we have gotten to be 4 degrees warmer. So our average rate of change here is 4, right? This is our change in temperature. Over our change in time. What are our units here? Well, on top we have a temperature, and underneath we have 1 hour, right? So our units here are 4 degrees Fahrenheit per hour. Usually when we write these units, we have the unit for Y per the unit for X. So here, degrees Fahrenheit per hour. What does this mean? Well, from 12 o'clock to 1 o'clock, the temperature increased on average by 4 degrees per hour. Well, that wasn't super useful because that was just 1 unit of time. Let's see what happens when we do more than 1 unit of time. So what is the average rate of change between 1 and 4:30? So let's do this again. At 1 o'clock, we're at 1 hour. At 4:30, we're at 4.5 hours. So between 1 o'clock and 4:30, 3.5 hours have passed, right? Our temperature at 4:30 is 93, and our temperature at 1 is 82. We calculate this, and we end up with 11. So our change in temperature is 11 degrees, right? We've gotten 11 degrees hotter over that time, and that time is 3.5 hours. So we calculate this, we can put it into our calculator, we end up with 3.143. And our units there, again, are degrees per hour. Right, if you want to, you can write it out per hour. You could also do, degrees over an hour, right? Sometimes per is written with a slash like this. Either is totally fine. Let's write this out in a sentence. What does this mean? Well, from 1 o'clock to 4:30, the temperature increased on average by 3.143 degrees per hour. Right, so as we move from 1 o'clock to 2 o'clock, we increase by about 3.143 degrees. As we move from 2 o'clock to 3 o'clock, we increase by another 3.143 degrees, right? And same thing until 4. And then as we get to 4:30, we increase by about half of this, right? Because we've only been able to move forward half an x value, so we only get to move up half of this, right? So that's what's going on here. Why don't you guys try this last one from 4:30 to 6? And make sure you interpret it in the context of the problem. So write a sentence about what it means. Okay, so I put in 91 degrees for 6 o'clock and 93 degrees for 4:30. We ended up getting negative 1.333 degrees per hour. That means that from 4:30 to 6 o'clock, the temperature decreased on average by 1.333 degrees per hour, right? It's decreasing by that much because it's negative, right? We're getting smaller. Our temperature is getting lower. We won't need to do D either. Okay, that's all I have for average rate of change. Hopefully this makes sense. You'll have opportunities to practice average rate of change graphically as well as symbolically and then with word problems in Desmos. Okay, thanks for watching.